What are binary search trees? Binary search trees, or BSTs, are a form of binary tree which have a special ordering property. Elements to the right of any given node are greater, and elements to the left are smaller. In the case of equal to, it depends on the implementation. Binary trees are extremely useful because it makes it very quick to find elements. This is an example of a BST. If you notice, the nodes to the right of the parent node are larger, and the nodes to the left are smaller. Say we want to get to 22. We would start at 20, and then, since 22 is larger than 20, we'd know to go to the right. Then that takes us to 25. Since we know that 22 is smaller than 25, we'd go to the left, and then we end up at 22. See how quick and easy it is to find elements in a binary search tree? Here we have a tree that is not a BST. That is because this element 16 does not follow the ordering property. Because 16 is less than 20, we know that in a BST, it shouldn't be to the right of it. This is just one example of why it's not a BST. Alright, let's take a look behind the scenes to see what's happening. BSTs, like other binary trees, are made out of nodes. Right here we have our root node. The root node points to the top of the tree. Because our tree is empty, it points to null. Then we add 10. A new node is created and the root points to 10. Then we add 15. We see 15 gets added to the right of 10 because it is larger than 10. Then we add 2. Since 2 is smaller than 10, it gets added to the left. Now we add 6. 6 is less than 10, so we go to the left. And 6 is greater than 2, so we add 6 to the right child of 2. And now let's add 20. Because 20 is larger than 10, we go to the right. And 20 is larger than 15, so we add 20 to the right child of 15. Finally, let's add negative 4. Negative 4 is less than 10, we go to the left. And negative 4 is also less than 2, so we add negative 4 to the left child of 2. Now suppose we wanted to remove 6. All that would happen is 2's right child would be set to null, and 6 is then cleared from memory. A leaf node is easy to remove. That being said, to get rid of any confusion, I'm going to get rid of the null, because we already know that all empty pointers are considered pointing to null. Then say we want to remove 2. Since 2 only has one child, we set 2's parents to point to 2's only child, and then 2 gets removed from memory. Easy enough. But say we wanted to remove 10, what would happen? 10 has 2 children. Typically what happens is it is replaced with whatever the in-order successor is. In other terms, we take the leftmost value of the right subtree of 10. So we go to 15, which is the right subtree of 10. And then we realize that 15 has nothing to the left of it, meaning that it is the smallest value in 10's right subtree. Therefore, we replace 10 with 15, and then point 15's left child to negative 4, and right child to 20. There is an inherent flaw with binary search trees, however. Suppose we wanted to use a binary search tree to store some integers. We add 1, then 2, then 3, then 4, then 5. If you notice, this doesn't really look like a tree. Instead, it looks more like a linked list. This is because this tree isn't balanced, meaning that this data will not be able to take advantage of the efficiency that binary search trees can offer. This occurred because we added the elements in numerical order, an unlikely event, but it is still something to note. And that's all you need to know to understand the basics of binary search trees. If you enjoyed it, feel free to like and subscribe. Thank you for watching.